What lies beneath everything we can see? Beneath the stars, beneath the cells, beneath the dust motes that dance in a sunbeam. What truly forms the fabric of existence? For centuries, humanity has peeled back the layers of the world like pages of an endless book, believing each discovery would reveal the final sentence, the smallest, indivisible piece of reality. Yet every time we think we've found the bottom, it crumbles into something deeper. Once, the atom was sacred. The word itself means uncuttable. But we cut it anyway, and found within it a storm of smaller worlds. Protons, neutrons, electrons spinning in invisible orbits of probability. We thought that was the end, until we saw that even those were made of quarks, tiny vibrating points of unimaginable density. And beyond the quark, silence, uncertainty. The smaller we look, the less we find, until reality itself starts to vanish. Space is no longer smooth or solid, but foamy, trembling, filled with fluctuations of energy that flicker in and out of existence. At scales beyond comprehension, the universe ceases to behave like matter at all. It becomes pure mathematics, pure vibration, a dance of information flickering at the edge of being. So we ask again, does the universe ever stop dividing? Is there a final grain of reality, a last indivisible note in the song of existence? Or is smallness itself an illusion, an infinite descent into deeper mysteries? If we could see the smallest thing, perhaps we wouldn't just find a particle. Perhaps we'd glimpse the code that wrote reality itself, and discover that the universe, at its most fundamental level, might not be made of things at all, but of thought. If all the atoms in your body lost their empty space, you could fit inside a single grain of sand, the weight of a person, compressed into something almost invisible. It sounds impossible, yet it's a quiet truth hidden inside every breath, every heartbeat, every star. Matter, as it turns out, is mostly nothing. But to understand how we discovered that astonishing emptiness, we must return to an age when the world still seemed solid, when philosophers believed that reality could be sliced only so far before reaching the final, unbreakable seed of being, the atom. It began more than 2,000 years ago, in the mind of a Greek philosopher named Democritus. He had no microscope, no laboratory, only imagination. He envisioned reality as a grand tapestry woven from countless tiny, invisible grains. He called them atomos, meaning uncuttable. To him, the universe was built from these eternal, indestructible blocks moving through the void. It was a radical idea, one that stripped creation of divine intervention and replaced it with endless motion and chance. The cosmos, he said, was not crafted by gods, but by collisions. Everything, from stone to soul, was made of the same invisible dust. For centuries, his idea drifted like a forgotten seed. Aristotle's vision of a continuous element-based world, earth, air, fire, water, took root instead, shaping science for nearly 2 millennia. But the silence of the atom didn't mean it was gone. It waited, sleeping beneath centuries of belief, until the dawn of the modern age. In the early 1800s, an English schoolteacher named John Dalton resurrected the old dream. Using chemistry rather than philosophy, he noticed patterns, gases combined in simple ratios, weights multiplied neatly, as if matter came in discrete packets. Dalton dared to suggest that Democritus was right, that the world was built from indivisible atoms, each element defined by its unique kind. To Dalton, hydrogen, oxygen, and carbon were the alphabet of nature, spelling out everything from water to flesh to flame. His vision brought order to the chaos of chemistry. For the first time, atoms became not just ideas but measurable realities. Scientists began to imagine these atoms as tiny billiard balls, solid and eternal, colliding to form everything we could see. The picture was clean, comforting, a universe built from perfectly hard, indivisible marbles. But comfort never lasts long in science. As tools improved, the marbles began to crack. By the late 19th century, strange new clues appeared. Electricity, a mysterious current of invisible force, seemed to pass through matter as though it were partly hollow. In 1897, a quiet man named J.J. Thomson performed an experiment that shattered the old atomic ideal forever. Using a cathode ray tube, he discovered something smaller than the atom itself, a particle carrying a negative charge, later called the electron. The indivisible atom was divisible after all. Reality, once thought solid, had fractured again. Imagine the shock of that moment. Centuries of certainty undone by a flicker of light in a glass tube. Thomson proposed a new model, the plum pudding atom. Electrons, he thought, were embedded like raisins in a sphere of positive charge. It was imperfect, but it marked a revolution. The atom was no longer the final frontier, but a miniature universe in itself. Then came Ernest Rutherford, a man who would blow that universe wide open. In 1911, he conducted what seemed like a simple experiment, firing alpha particles at a thin sheet of gold foil. According to the plum pudding model, those particles should have passed through with only gentle deflections. But to Rutherford's amazement, a few bounced backward, as if hitting something dense and invisible. It was as if you fired a shell at tissue paper, he said, and it came back and hit you. From that shock, a new vision emerged. Rutherford realized that nearly all the atom's mass, and its positive charge, must be concentrated in a tiny central core, the nucleus. The rest was almost entirely empty space. The atom, once imagined as a solid sphere, became a vast cathedral of emptiness, with a minuscule sun at its center and electrons whirling far away in ghostly orbits. If an atom were enlarged to the size of a football stadium, the nucleus would be a grain of rice at the center, and the electrons would circle near the stands, leaving everything else completely void. The solidity of the world around us, the hardness of stone, the weight of mountains, is nothing but the illusion of electromagnetic forces keeping these empty shells from collapsing into one another. We live inside a universe of almost perfect emptiness that merely feels full. This revelation changed more than physics. It changed philosophy itself. The very notion of substance began to dissolve. What, after all, does it mean for something to exist if it is mostly nothing? The wall you touch, the chair you sit on, your own hand. All are made of atoms whose cores never touch, held apart by invisible fields of energy. Matter became a story not of solid things, but of interactions, forces, relationships. The atom, once a symbol of finality, now revealed a paradox. Every discovery that seemed to mark an end Democritus's atom, Dalton's billiard balls, Thomson's pudding, Rutherford's nucleus became only another beginning. The smaller we looked, the more our certainty crumbled. In the wake of Rutherford's revelation, Niels Bohr refined the picture again. He imagined electrons orbiting the nucleus like planets around a sun, leaping between energy levels in quantum jumps. It was elegant but not complete. Soon, quantum mechanics would dismantle even this planetary metaphor, replacing orbits with clouds of probability, shimmering fields of possibility rather than fixed paths. Yet in the age of the atom, that storm of discovery felt like a triumph. Humanity had reached down into the invisible and found order where once there was myth. The structure of the universe was no longer the domain of gods, but of equations. The secrets of chemistry, radiation, and even the energy of the stars were hidden within this new understanding. From that knowledge came both creation and destruction, the power to illuminate cities or annihilate them in an instant. The atom became both symbol and warning. The smallest things could hold the greatest consequences. Still, beneath the celebration lingered an unease. Each revelation only deepened the mystery. If atoms were mostly empty, what held them together? If their nucleus was so dense, what composed it? Scientists soon learned that the nucleus itself contained smaller constituents, protons and neutrons, bound by a force unimaginably strong. And even these, they would discover, were not the end. The pattern of history repeated. Every indivisible truth fractured into smaller truths, each one stranger than the last. The age of the atom had promised a final foundation, a bedrock beneath the chaos. Instead, it opened a chasm, a realization that there might be no end to smallness at all. The atom, far from being the ultimate building block, was a doorway to deeper infinities. Philosophers began to ask new questions. If matter is mostly void, is reality more absence than presence? Is the universe made of things, or merely the relationships between them? Perhaps the illusion of solidity, the comfort of touch, is the mind's way of interpreting a sea of interactions too subtle to perceive. Every time we found an end, it became a beginning. Democritus's dream of eternal atoms had survived, but transformed. We no longer imagined matter as unbreakable dust, but as patterns of energy dancing through emptiness. The deeper we looked, the more we realized there is no smallest piece, no final boundary, only endless descent. In the glow of early 20th century laboratories, humanity stood at the edge of that realization, gazing into the hollow heart of existence. The atom had once promised certainty. Now it whispered something else, that the universe might not be built from things at all, but from an infinite play of possibilities. The journey inward had only begun. Beneath the nucleus waited new secrets, particles smaller, stranger, more fundamental. The solid world we thought we knew had dissolved into fields and forces, into flickering patterns of energy where substance once seemed to reside. And as we peered deeper into that emptiness, a new era was about to dawn, one that would question not just what the world is made of, but whether anything truly is at all. At the smallest scales, matter disappears, replaced by possibility. What we once imagined as solid, indivisible specks of being dissolve into something stranger. Waves that are not waves, Particles that are not particles, flickering in and out of existence like whispers between two worlds. It is here, in the quantum realm, that the universe stops behaving like a machine and starts behaving like a dream. When scientists first began to peer beneath the atom, they expected to find smaller marbles, tinier gears in the cosmic clockwork. But what they found instead defied all logic. Electrons, once pictured as miniature planets orbiting the nucleus, refused to stay in place. They did not trace clean paths, nor did they exist in any single location. The more precisely you tried to measure where one was, the less you could know about its motion. The more clearly you saw its speed, the more it seemed to vanish from space entirely. This strange dance of uncertainty was not a flaw in our instruments, but a fundamental feature of nature itself. Werner Heisenberg captured this paradox in 1927 with his uncertainty principle, a law not of ignorance, but of existence. At the quantum level, reality does not allow exactness. Position and momentum are not merely unknown, they are undefined. The world beneath the atom is not a stage filled with objects, but a field of pure potential, a shimmering haze of possibilities waiting to become real. This was the end of the old mechanical universe, the one Newton had built on certainty and predictability. Here, cause and effect were blurred. The same particle could pass through two places at once, could interfere with itself like a ghost, could exist in multiple states until forced to decide by the mere act of being observed. The quantum realm made no sense, and yet every test, every experiment confirmed its truth. The most famous of these is the double-slit experiment, a simple setup with impossible consequences. Shine light through two narrow slits onto a screen, and you see an interference pattern. Bright and dark bands, like waves overlapping in a pond. Light clearly behaves like a wave. But when you send individual photons, particles of light, one at a time, the pattern remains. Even when only one photon passes through, it seems to interfere with itself. How can one particle pass through both slits at once? When scientists placed detectors to watch which slit each photon used, the interference vanished. The photons acted like particles again. The mere act of observing them changed the outcome. At that moment, the universe seemed to flinch under our gaze. Observation created reality. Before the measurement, each photon existed as a cloud of probabilities. It might go through the left slit. It might go through the right. Only when observed did it choose. Nature, it seemed, was not made of definite things, but of possibilities that solidify only when looked at. What, then, does it mean for something to exist? If a particle's position is undefined until measured, is it real before we look? Quantum mechanics suggests that the universe itself may be woven not from matter, but from information, a set of probabilities that crystallize into form through interaction. The cosmos, at its core, is not a sculpture, but a song. Not a fixed object, but a pattern of vibration. The wave function, that elegant mathematical ghost introduced by Schrödinger, describes every possible state a particle could occupy. Left unobserved, it spreads like a ripple through space, encompassing countless possibilities. But the moment it interacts with an instrument, a photon, a conscious observer, the wave function collapses. The infinite potential becomes a single outcome. Reality, in this sense, is the universe deciding moment by moment, which of its infinite possibilities to make visible. In this strange new world, particles can be entangled, linked so intimately that a change in one instantly affects the other, even if they are separated by light years. Einstein called it spooky action at a distance, because it seemed to defy his theory of relativity. Yet experiments have proven it beyond doubt. Entangled particles share a single quantum state. They are one system spread across space. Measure one, and the other knows instantly, faster than light. It's as if the universe itself refuses to be broken into parts, as if every bit of it remains connected in an invisible web of information. The quantum realm does not fit neatly into the human imagination. We evolved to throw spears, not to grasp probability clouds. But its rules shape everything. The way electrons dance around atoms, the way stars burn, the way your neurons fire. Even the solidity of your body is an illusion born of quantum forces. The electrons in your skin never touch the electrons in the chair you sit on. They repel each other through electromagnetic fields. You are hovering, always, a microscopic distance above everything you touch. A ghost, made tangible only by the resistance of quantum energy. Think about that. You have never truly touched another thing. The firmness of a handshake, the ground beneath your feet, the texture of the world. All are interactions of invisible fields, patterns of probability colliding but never merging. Your body is a symphony of quantum events, a cloud of vibrations that coheres only long enough to be called you. At times, quantum mechanics feels less like physics and more like philosophy in disguise. Niels Bohr, one of its founders, once said, "If quantum mechanics hasn't profoundly shocked you, you haven't understood it yet." Because to understand it is to face a universe that refuses to exist in the way we imagine it should. The notion of things dissolves. The world is no longer built from blocks, but from behaviors. Not matter, but mathematics. Not particles, but probabilities. This realization brings both awe and dread. Awe, because the fabric of existence is alive with infinite possibility. Dread, because that same fabric seems to vanish when we try to grasp it. The closer we look, the more reality recedes, leaving behind a shimmer of potential, a whisper of something that may or may not be. The universe, it seems, hides behind its own uncertainty, revealing itself only through interaction, through attention. Consider again the double-slit experiment. Each photon's path is undefined until we look. But what counts as looking? Must it be a conscious mind, or is any interaction a detector, a molecule, a flash of light, enough? Some physicists suggest consciousness itself collapses the wave function, that awareness is the bridge between the possible and the actual. Others argue that observation is just physical measurement, that the universe doesn't care who's watching. But even then, the question lingers. If no one ever measured anything, if nothing ever interacted, would the universe exist at all? In quantum theory, existence is not a static property, but a process, an ongoing negotiation between the possible and the actual. The world is not there waiting for us. It becomes as we engage with it. This idea echoes ancient philosophies, from Buddhist notions of dependent origination to the idealism of Berkeley, who claimed that to be is to be perceived. Science, once the enemy of mysticism, now circles back to its doorstep. But quantum mechanics does not ask us to abandon reason. It asks us to expand it. The equations work flawlessly. They predict the behavior of particles, the spectra of atoms, the structure of matter. The weirdness is not a flaw, but a feature of a reality deeper than intuition. Beneath the surface chaos lies astonishing precision. The world may be uncertain, but it is never random. One of the most haunting ideas born from this precision is quantum tunneling, the ability of particles to pass through barriers they seemingly shouldn't. In our macroscopic world, walls stop us and boundaries define us. But in the quantum world, no wall is absolute. A particle, described by its wave function, always has a chance, however small, to appear on the other side. The universe, it seems, does not obey impossibility. It obeys probability, and from that probability, everything arises. Stars ignite, because quantum tunneling allows protons to overcome their mutual repulsion and fuse. Life exists because atoms can share electrons in probabilistic dances of bonding. Even the stability of the universe depends on the uncertain trembling of the quantum vacuum, a sea of virtual particles appearing and vanishing everywhere, every moment. This vacuum is not emptiness. It is the most active thing in existence, a restless field of pure potential. In that seething foam, particles are constantly born and destroyed, lending energy to the fabric of space-time itself. From this quantum chaos, galaxies form and black holes evaporate. What we call nothing may be the most fundamental something of all. And so the question deepens. If the universe at its smallest level is not made of things, what is it made of? Some say information, the bits and qubits of a cosmic computation. Others say energy, vibrating in higher dimensions like strings of an unseen instrument. Perhaps both are true, or perhaps neither. Perhaps made of is the wrong question altogether. The quantum realm reminds us that reality may not be a noun, but a verb, not a structure, but an act of continual becoming. When you look at your hand, you see solidity, continuity. But beneath that illusion lies a storm. Electrons flickering in and out of existence. Quarks trembling in probabilistic confinement. Virtual particles bursting and dying in the vacuum that fills the space between them. Your hand, the stars, the universe, all are ripples in a field that cannot be seen, only felt through its effects. You are not made of matter. You are made of motion. The philosopher Erwin Schrödinger, who gave us the famous cat that is both dead and alive, once said, "The total number of minds in the universe is one." In the quantum realm, it's easy to see why. Everything is connected through shared uncertainty, woven together by the rules of probability. To exist is to participate in the grand computation of being. At this scale, there are no borders, only probabilities entangled across space and time. The universe is not built like a wall of bricks, but like a web of relationships. Matter is what happens when fields interact, when waves cross and momentarily stabilize into form. Even you, the observer, are part of that process. The act of asking, "What is real?" becomes inseparable from reality itself. And perhaps that is the ultimate paradox. The more we seek to grasp the smallest thing, the more we find ourselves woven into the answer. The universe without solids becomes a mirror, reflecting the mind that looks into it. Reality, it seems, is not something we observe from the outside. It is something we awaken within. At the smallest scales, the cosmos whispers its secret. There are no solid walls, no firm foundations, only possibilities trembling into being. Every atom of your body, every particle of light in the sky, every fluctuation in the void is part of an eternal unfolding, a continuous act of becoming. The quantum realm is not beneath reality. It is reality. And everything else is its dream. Every second, trillions of ghost-like particles stream through your body, passing through walls, air, and flesh, as if none of it were there. They come from the heart of the sun, from exploding stars, from the very birth of the universe itself. You never feel them. You never see them. They are neutrinos, elusive messengers of a world beneath the visible, where matter dissolves into a restless orchestra of energy and symmetry. This is the subatomic zoo, the realm of quarks, leptons, bosons, and the strange forces that choreograph their eternal dance. For centuries, humans believed the atom was the ultimate building block. Then we split it and found the nucleus. We smashed the nucleus and found protons and neutrons. We cracked those open and found something smaller still. The quarks. These quarks are not tiny marbles. They are excitations, pulses in invisible fields that fill all of space. In this world, nothing is truly solid or isolated. Every particle is a fleeting vibration, a musical note in a cosmic symphony that never ends. Physicists call this great pattern the Standard Model, the most successful theory in the history of science. It describes 17 fundamental particles that make up everything we have ever observed, from the smallest grain of dust to the largest galaxy cluster. Organized with mathematical elegance, these particles fall into two great families: fermions, which make up matter, and bosons, which carry the forces that bind it together. The fermions are the builders. They include 6 quarks and 6 leptons, arranged in 3 generations, each heavier and more unstable than the last. The up and down quarks form the familiar protons and neutrons in every atom's heart. The strange and charm quarks, the top and bottom quarks, heavier, rarer, more ephemeral, emerge only in the high-energy collisions of stars and particle accelerators. Alongside them, the leptons, the electron that orbits atoms, the muon and tau that mimic it at higher masses, and their ghostly partners, the 3 neutrinos, nearly massless, invisible, streaming endlessly through the cosmos. The bosons are the mediators, the carriers of the forces that give the universe its structure. The photon governs electromagnetism, binding light and electricity into one elegant phenomenon. The gluons hold quarks together inside protons and neutrons, stitching them with the strong nuclear force so intense that no quark can ever escape alone. The W and Z bosons carry the weak nuclear force, responsible for radioactive decay and the nuclear alchemy that powers stars. And then there is the Higgs boson, the last to be discovered, the quiet architect of mass itself. In this hidden architecture, mass is not a thing, but an interaction. The Higgs field, invisible and omnipresent, fills all of space. Particles gain mass by interacting with it, like swimmers moving through thick water. The stronger their coupling to the Higgs field, the heavier they become. Photons glide through it without resistance, remaining massless and free. The top quark, in contrast, wades through it like a boulder, heavy and reluctant to move. Mass, then, is not an inherent quality. It is resistance to change, a kind of cosmic friction between existence and the field that sustains it. This discovery redefined what it means for something to exist. We once imagined particles as fundamental things, but now we see them as patterns, ripples in a web of fields that fill the vacuum. Every particle is a temporary disturbance, a crest on an invisible ocean of energy. When you strike a violin string, a note emerges, vibrates, fades, yet the string remains. The universe, too, is a vast instrument, and matter is its music. The Standard Model is the sheet music of that symphony. Written not in notes but in equations, it encodes the harmonies of the fundamental forces. Its symmetries are breathtaking, mathematical patterns that suggest a deeper unity behind all diversity. The gauge symmetries of the strong, weak, and electromagnetic forces are like the different keys of a cosmic melody, each governing its own domain but resonating in perfect mathematical proportion. But this harmony is not immediately visible. To hear it clearly, one must reach energies high enough to strip away the superficial layers of mass and distinction. In the searing early moments of the universe, just after the Big Bang, the forces we now see as separate were one. Electromagnetism and the weak force were united as the electro-weak interaction, until the cooling universe broke their symmetry. It was this breaking, this shattering of perfect balance, that gave particles their individuality. Mass emerged as the symmetry fractured, and from that fracture, the world as we know it was born. Still, even this grand theory leaves mysteries unresolved. The Standard Model, for all its precision, cannot explain everything. Gravity, the oldest and most familiar of all forces, is absent from its equations. Nor does it explain dark matter, the invisible substance that outweighs visible matter 5-to-1, or dark energy, which drives the expansion of the cosmos. The model is exquisite and incomplete. It describes the notes, but not the composer. To understand its depths, we must step inside the forces themselves. The strong force carried by gluons binds quarks so tightly that no individual quark has ever been seen in isolation. This confinement is absolute. As you try to pull quarks apart, the energy between them grows until it becomes enough to summon new quarks from the vacuum. It is as if the universe forbids loneliness at the smallest scales. Every proton, every neutron, is a tiny prison of eternal companionship. The gluons that bind them together also interact with each other, weaving an inescapable knot of self-reinforcing energy. This is why the heart of matter is so dense, why atomic nuclei resist disintegration until struck by forces vast enough to mimic the conditions of the early universe. In contrast, the weak force operates on a different rhythm, delicate, ephemeral. It is the reason the sun shines, the mechanism behind nuclear fusion. Deep within the sun, protons are transformed into neutrons through the exchange of W and Z bosons, releasing neutrinos and light. This process converts mass into energy, fueling the stars and, ultimately, life itself. Without the weak force, hydrogen would remain forever unchanged, and the cosmos would be dark and still. And then there are the neutrinos, those invisible travelers that pass through everything. Born in nuclear reactions, they rarely interact, slipping through light years of matter without a single collision. Yet they carry secrets about the universe's earliest moments. Some physicists suspect that neutrinos hold the key to why the cosmos contains more matter than antimatter. In their ghostly silence, they may hide the story of why we exist at all. The quantum fields that define these particles extend everywhere, even where the particles are not. The electron field fills all of space. When it vibrates in a particular way, we perceive an electron. The photon field, when excited, becomes light. In this sense, the universe is a sea of fields, and what we call particles are simply the visible ripples in that sea. The vacuum is not empty. It is the most dynamic place in existence. Every cubic centimeter of nothing teems with invisible fields, restless with potential energy. This picture challenges the very language we use to describe reality. If everything is a field, then what are we? Collections of localized excitations, coherent vibrations temporarily organized into patterns that think and feel? You are not made of particles, but of harmonies, overlapping waves in a cosmic song. And when those waves lose their coherence, when the pattern fades, the fields remain, forever humming in the background. Matter is temporary. The music never ends. Still, the Standard Model, for all its beauty, is haunted by questions it cannot answer. Why these particles and not others? Why 3 generations of quarks and leptons? Why such vast differences in their masses? Why does the Higgs field have the strength it does? Not more, not less. A balance so precise that if it were slightly different, the universe could not hold atoms, stars, or life. Some physicists believe there may be deeper symmetries yet unseen. Supersymmetry, perhaps, where every known particle has a hidden partner. Or theories that unite all forces in a single elegant equation. But for now, the Standard Model stands as our best map of the invisible, a cathedral of mathematical truth erected in the void. And yet, beyond its perfection, looms an unsettling thought. If particles are ripples in fields, what are fields made of? The question seems innocent, but it strikes at the core of existence. A field is not a substance that occupies space. It is space, or rather, the potential within space for things to manifest. It has no texture, no color, no boundary. It cannot be scooped, touched, or seen. It is pure relationship, a network of possibilities. The field exists because interactions do. Without interactions, it would be meaningless. Perhaps fields are the universe's way of storing possibility, a hidden scaffolding for reality itself. Every vibration, every flicker of a quark or electron is the universe expressing a choice, a local affirmation of being. When we ask what the field is made of, we are really asking what existence itself arises from. And maybe that question cannot be answered within the same frame that asks it. In a sense, the Standard Model has revealed both everything and nothing. It explains nearly all visible matter and energy, predicts the results of experiments with uncanny precision, and yet leaves untouched the deeper mystery of what reality is. It is as if we have decoded the notes of a cosmic song, but do not yet know who or what is playing it. So we stand at the edge of knowledge, surrounded by invisible seas of fields, haunted by unseen symmetries, and warmed by the silent rain of neutrinos streaming through our bones. We have learned that mass is an illusion of interaction, that matter is a pattern in motion, that particles are not things but vibrations. And as we peer deeper into the subatomic zoo, we begin to realize that the question is not how small the universe can get, but how deep. For if every particle is a ripple, every field a vibration, then perhaps beneath it all lies not substance, but song. The cosmos may not be built of matter at all, but of meaning, the endless play of structure and symmetry, of energy becoming awareness through the act of existing. In the end, the Standard Model is not just a map of the subatomic world. It is a glimpse into the poetry of creation itself, the hidden order that hums beneath reality's silence. Below a certain size, there is no smaller, because there is no space left to be small in. It is one of the strangest, most humbling boundaries ever conceived by the human mind. The Planck length, a scale so incomprehensibly tiny that our very language dissolves when we try to describe it. At roughly 1.6 times 1035 meters, it stands as the smallest meaningful distance in the universe. A wall not made of matter, but of meaning itself. Beyond it, the smoothness of space breaks apart. Geometry, time, and causality, the very grammar of reality, begin to stutter and fail. The Planck length is the edge of the known and the beginning of the unknowable, where even the concept of place loses its meaning. To approach it, we must descend through magnitudes of smallness so vast they defy imagination. A human hair is about 10 to 4 meters thick. A single atom measures around 1010. The nucleus within it, 10 to 15. Inside that nucleus, quarks dance at scales near 1018. Each step down feels like crossing galaxies in reverse, shrinking through layers of structure until there is almost nothing left to measure. But at the Planck length, a strange thing happens. The act of measuring itself ceases to make sense. This limit arises from the marriage and the tension between the two greatest theories of modern physics, general relativity and quantum mechanics. Einstein's relativity describes gravity as the curvature of space-time, smooth and continuous, bending under the weight of mass and energy. Quantum mechanics, by contrast, reveals that everything else in nature, energy, light, matter, comes in discrete, jittering quanta. The Planck length is where these two pictures collide. Try to probe space at a scale smaller than this, and quantum uncertainty floods in with such violence that space-time itself would collapse into a black hole. It's a breathtaking paradox. The more precisely you try to observe the smallest things, the more energy you must use, and the more you warp the very fabric you're trying to study. Push that energy high enough, and the act of looking creates gravity so intense that it folds space shut. Observation becomes destruction. The universe, it seems, has built-in censorship, a final veil to protect its innermost workings. At this frontier, physicists speak of quantum gravity, the elusive theory that would reconcile the smoothness of Einstein with the jittering chaos of the quantum world. Though no one has yet seen it directly, hints emerge from thought experiments and mathematics. Space, at the Planck scale, may not be a continuous sheet, but a frothing sea of uncertainty. Physicist John Wheeler called it space-time foam, a restless landscape of micro-wormholes and flickering geometry, where distances and durations fluctuate violently. In this foam, up and down lose meaning. Before and after dissolve into shimmering probability. The universe, on its smallest canvas, is not built but born, constantly forming and unforming, too turbulent for any classical picture to survive. Imagine space-time not as a fabric, but as a storm. Energy whirls and folds upon itself. Tiny bubbles of curvature pop in and out of being. Microscopic black holes form and vanish within trillionths of a second. The geometry of reality itself becomes a quantum object. Uncertain, mutable, self-interacting. There is no solid background left on which events happen. The background is the event. The universe becomes self-referential, its structure arising from the same chaos it contains. If this sounds like poetry, it is because mathematics itself becomes poetic here. Our equations, once clear and stable, begin to blur. General relativity speaks of smooth curves, quantum mechanics of discrete jumps, but neither can describe a world where space itself is quantized. We are left with riddles. Is there a minimum distance, a smallest unit of volume, like the grain of a cosmic fabric? Or does the very notion of distance evaporate entirely? Some theories suggest that below the Planck scale, there is no below, that space ceases to be meaningful and must be replaced by something deeper. Pure information, pure relation, pure potential. Loop quantum gravity imagines space-time as woven from loops, indivisible quanta of geometry connected like threads in a cosmic network. String theory proposes something different, yet equally audacious, that the fundamental units of nature are not points, but tiny vibrating strings of energy, their harmonics giving rise to all known particles and forces. In string theory, what we call an electron is one note on the string's instrument, a photon, another. The quarks and gluons of the Standard Model are not distinct objects, but different vibrations of the same underlying filament. The universe, then, is not built from building blocks, but from melodies. The smallness of the Planck length corresponds to the shortest possible wavelength of these cosmic strings, the limit of vibration itself. Try to look closer, and the string's own energy curls space around it, preventing you from seeing beyond. The Planck scale is nature's ultimate self-containment, where inquiry and creation become the same act. It is here, too, that the concept of dimensionality begins to tremble. String theory requires not 3, but 10 dimensions of space, some curled so tightly that they vanish from our perception. These hidden dimensions may explain why the forces of nature differ in strength, or why gravity appears so weak compared to electromagnetism. They may even form the scaffolding on which space-time itself is built. But whether they exist as literal extensions or mathematical necessities remains a mystery. The deeper we go, the more reality seems to multiply into possibilities rather than simplify into truth. At the Planck wall, our greatest questions fold into paradox. What is time when each tick becomes meaningless? What is space when its continuity dissolves into quantum foam? The boundary between existence and non-existence grows thin. The equations that once described everything now contradict one another, and even logic begins to warp under the pressure. And yet, there is a strange beauty in that failure, because it means we are touching the limits of comprehension itself. To encounter the Planck length is to stand at the event horizon of understanding, looking into a realm where not just matter, but reality's rules themselves are fluid. The Planck wall is not a barrier of distance, but of definition. Beyond it, there may be no where, no when, no something. Only potential, shimmering and uncollapsed. Some physicists suspect that this smallest scale hides the secret of everything, that if we could decode the quantum structure of space-time, we would glimpse the unifying theory of nature. But others wonder whether there is even a structure to find. Perhaps space and time are not fundamental at all, but emergent, illusions born from a deeper informational layer. Just as temperature arises from the random motion of countless atoms, perhaps space-time arises from the entanglement of quantum information. A statistical mirage of something more primal. If this is true, then the Planck wall is not the smallest point in space, but the boundary between two realities. One we can describe, and one we can only imagine. On one side lies geometry, distance, and causality. On the other lies raw potential, a realm where every point contains every other, where the universe exists as pure possibility before resolving into form. It is not that space ends here. It is that space begins here, over and over again, born anew in each quantum fluctuation. Consider the implication. If the fabric of the cosmos is woven from information, then every particle, every photon, every galaxy is part of a grand computation. The universe processing itself. Space and time, then, are not the arena of reality, but the result of it. The Planck length marks the pixel size of existence, the smallest unit of resolution in the cosmic simulation, beyond which the screen itself dissolves into static. This image of space-time flickering like static captures the essence of the Planck frontier. It is not emptiness we approach, but the source of form. Beyond the wall, the distinction between matter and mind, energy and awareness, may cease to exist. Perhaps what we call physics is just one side of a larger coin, whose reverse is consciousness, the awareness through which the universe observes itself into being. The philosopher's question merges with the physicist's. If space is emergent, from what does it emerge? What breathes reality into the void? String theory, loop gravity, holographic models all attempt to capture fragments of that answer. They describe a universe where everything is connected by mathematical symmetries so deep they border on poetry. But beneath those equations hums a silence, a question no formula can contain. Why does anything exist at all? The Planck wall does not answer that question. It only shows us where to ask it. It tells us that smallest is not the end of the line, but the edge of comprehension, the threshold where our definitions collapse under the weight of what they try to describe. Beyond it lies no smaller world, but a deeper one, a realm without space or time, perhaps without separation, where being and nothingness are one and the same. So we stand before it, the final horizon of smallness, a boundary not of matter, but of meaning. The Planck length is the whisper beneath all creation, the place where existence flickers between yes and no, where reality hesitates before becoming. It is the ultimate paradox that the smallest thing in the universe is not a thing at all, but the absence that allows everything else to be. Every atom, every heartbeat, every flicker of thought, a note in the universe's endless song. Imagine that everything you've ever seen or touched, every star, every whisper, every cell in your body, is not made of solid particles at all, but of tiny, vibrating strings, each one a filament of pure energy, oscillating in patterns so intricate that they give rise to everything: light, gravity, time, and even life. This is the dream of string theory, that the universe, in all its vastness and complexity, is not a machine of matter, but a symphony of vibration. What if the smallest thing isn't a thing, but a sound? At first, this idea seems like poetry masquerading as physics. Yet when equations falter at the Planck scale, when space-time itself begins to foam and fracture, string theory offers a melody of coherence. Instead of point-like particles, infinitely small and problematically dense, it proposes that every fundamental constituent of the universe is a one-dimensional string, a loop of energy vibrating in multiple dimensions. Just as the tone of a guitar string changes with its tension and length, the properties of each particle, its mass, charge, and force, emerge from the frequency of its vibration. Quarks, electrons, photons, all different notes played on the same cosmic instrument. The beauty of the idea is overwhelming. It turns the chaos of the subatomic zoo into harmony. The discordant collection of particles and forces that populate the Standard Model could, in principle, all be manifestations of a single underlying reality. The strong, weak, and electromagnetic forces are simply different chords in the same composition, while gravity, the great outsider in modern physics, finds its place as a natural resonance of these vibrating strings. In this vision, the universe is not built from stuff, but from rhythm. Matter becomes music slowed to solidity. Space becomes silence between the notes. And energy, that restless hum at the heart of all being, becomes the eternal vibration that never stops. String theory, however, is not content with our familiar dimensions. For its mathematics to work, it demands more than the 4 dimensions we perceive. It requires 10, sometimes 11, with the extra ones curled up so tightly that we never see them, compactified into geometric forms of impossible beauty known as Calabi-Yau manifolds. These hidden dimensions may be the unseen harmonics that give rise to the visible universe. Just as the overtones of a violin string color its timbre, these extra dimensions may determine the fundamental constants of reality. The charge of the electron, the strength of gravity, the very structure of space-time itself. To explore these ideas is to wander through a landscape where geometry becomes melody. Picture it, a universe woven from vibrating filaments, each string looping through higher dimensions like threads in a tapestry made not of cloth, but of possibility. The strings twist, split, and rejoin, forming networks that hum with quantum energy. Their resonances interfere and reinforce one another, creating the illusion of particles, the persistence of form. And when these strings interact, they do not collide like billiard balls. They merge and exchange vibrations, producing the delicate choreography that gives rise to forces. Gravity, in this context, is not a curvature imposed upon space-time, but the collective low-frequency hum of all strings in concert, the bass note of existence itself. Some theories extend this idea into M-theory, a grander framework that suggests strings are not alone. Beneath them may lie membranes, brains, vast multidimensional surfaces upon which universes can form like bubbles on a cosmic sea. In this picture, our universe might be a single 3-dimensional brain floating in a higher dimensional expanse, occasionally brushing against others. Every collision, every cosmic chord struck across dimensions could trigger a new Big Bang, a fresh burst of creation in the endless music of being. It's an idea as dizzying as it is beautiful. If it's true, the universe we know, stars, galaxies, life, is just one melody among countless others echoing across a multidimensional orchestra. The cosmos is not one song, but a symphony without beginning or end, its harmonies forever shifting, evolving, reverberating, yet, for all its elegance, string theory remains a theory, untested, unconfirmed, and, for now, beyond the reach of experiment. The energies required to probe the Planck scale, where strings reveal themselves, are far greater than anything our technology can achieve. The Large Hadron Collider, mighty as it is, barely brushes the foothills of that realm. Still, string theory's mathematics sings with such consistency that many physicists believe it must contain a kernel of truth. It has become less a theory and more a language, a way to speak of reality where words fail. But there is another contender in this search for quantum gravity, one that trades vibrations for geometry, loop quantum gravity. Unlike string theory, it does not add dimensions or entities. Instead, it takes space-time itself and quantizes it, suggesting that space is woven from loops, finite, discrete rings of gravitational field. Picture an infinite web of tiny loops, each one a quantum of area, interlinked and vibrating subtly. This network, called a spin foam, defines the very texture of reality. Where we see smoothness, loop theory sees granularity, the grain of the cosmos itself. In this vision, the universe is not continuous, but pixelated, composed of indivisible units of space and time. The smooth curves of Einstein's space-time emerge only when billions of these loops interlace, like threads forming the illusion of a continuous fabric. Gravity, then, is not a force transmitted through space, but the geometry of the loops themselves. The curvature of space-time is simply their collective configuration, bending and flowing as the universe evolves. Loop quantum gravity and string theory seem like opposites, one built on geometry, the other on vibration, yet both converge on the same revelation, that the universe is not made of matter, but of relationships. Both imply that what we call existence is the interplay of patterns, the coherence of countless connections dancing in mathematical time. The smallest thing, it turns out, is not a thing at all. It is a process, a rhythm, a relationship. To grasp this is to step beyond physics and into philosophy. If everything is vibration, then what vibrates? If all is geometry, what draws the lines? Perhaps these are the wrong questions. Perhaps vibrating and being are one and the same. Existence as motion without mover, music without musician. The strings do not play a tune. They are the tune. The loops do not outline space. They are space. The universe may be pure self-expression, energy folded upon itself, singing the song of its own being. There is an ancient echo in this vision. Philosophers and mystics have long spoken of the music of the spheres, the harmony underlying creation. Pythagoras believed that numbers and ratios, the mathematics of vibration, were the foundation of all beauty and order. In the East, the sacred sound Om was said to be the vibration from which the cosmos arose. Now, physics, in its own language, seems to circle back to the same truth, that everything is frequency, resonance, rhythm. The universe does not contain music. It is music. Consider your own body through this lens. The atoms in your skin are composed of quarks bound by gluons, ripples in quantum fields. Those fields may, in turn, be the vibrations of strings, tiny loops of energy that have persisted since the dawn of time. Your heartbeat, your thoughts, your memories, all are patterns in that cosmic vibration. You are not separate from the universe's song. You are one of its notes, vibrating in harmony with everything else. When you speak, when you breathe, when you dream, you participate in the rhythm that has no beginning and no end. At this level of understanding, individuality begins to blur. The self is no longer a fixed point, but a resonance within a larger field of being. Matter, mind, energy, and consciousness become harmonics of the same underlying melody. The cosmos, it seems, is less like a machine to be dissected and more like a symphony to be heard. And perhaps this is why the deepest scientific truths feel poetic. When we speak of strings vibrating in 11 dimensions, or loops weaving space-time into granular geometry, we are not just describing equations. We are describing wonder. We are translating the ineffable into symbols, the silent music of existence into human understanding. The closer we listen, the more we realize that we are hearing ourselves reflected. The universe discovering its own rhythm through us. In the end, whether through strings or loops, frequencies or geometry, the message is the same. Unity, all diversity, all form, all motion, all thought arise from a single underlying order. One field, one vibration, one infinite song expressing itself through countless variations. So when you gaze at the night sky, when you see galaxies spiraling, stars pulsing, and light rippling across the void, remember, you are not looking at something separate. You are witnessing the great music of existence, the vibrations that have been echoing since the beginning of time. Every photon that reaches your eye, every atom in your heart, is part of that same symphony. Matter and meaning, intertwined in a dance of eternal resonance. The smallest thing in the universe, it turns out, is not a particle, not a string, not a loop, but the vibration itself, a tremor of being that ripples through everything, holding galaxies and souls in the same rhythm. The universe does not play the music. The universe is the music, and in the brief moment that you exist, you are its melody. The emptiest place in the universe contains infinite energy. What we call nothing is not an absence. It is an ocean, silent, invisible, yet boiling with creation. Even in the darkest, coldest corners of space, where no light shines and no particle seems to move, the vacuum hums with restless motion. This is the quantum vacuum, the background fabric of existence, the foundation upon which everything stands. And it is not empty at all. The story of this strange nothingness begins with a paradox. In classical physics, the vacuum was simple, the void, a stage upon which matter and energy performed their cosmic dance. Space was an empty container, a nothingness that simply was. But when quantum mechanics arrived, it shattered that serenity. According to the quantum view, even the absence of particles cannot be truly empty. Uncertainty forbids stillness. The more you try to quiet the universe, the more violently it trembles beneath your observation. At the subatomic level, this trembling takes the form of fluctuations, tiny surges of energy that appear and vanish in unimaginably short spans of time. These fluctuations give rise to virtual particles, ghostly twins that flicker into being in pairs, exist for an instant, and then annihilate each other back into nothing. They are called virtual, not because they are unreal, but because they never persist long enough to be directly measured. Yet their influence is everywhere. They alter the energy levels of atoms, shift the orbits of electrons, and even define the strength of fundamental forces. Every cubic centimeter of vacuum, if measured by quantum theory, contains a vast sea of these flickering pairs, particles and antiparticles bursting forth and collapsing again in an eternal rhythm. This sea is so energetic that, according to some estimates, the density of the vacuum should be enormous, enough to tear the universe apart. But somehow, most of this energy cancels itself, leaving behind a faint residue, a subtle pressure we now recognize as dark energy. It is this hidden energy of the vacuum that drives the universe to expand faster and faster, pushing galaxies apart as if space itself were exhaling. The emptiest void is the most active substance in existence. We live suspended within it, bathed in its invisible fluctuations. The air between your hands, the silence between atoms, even the gap between galaxies, all of it shimmers with potential. At every moment, the vacuum is testing possibilities, creating miniature universes that flicker out before they can be born. These ephemeral sparks are the fingerprints of a restless cosmos, forever unable to sit still. This constant dance has measurable consequences. The Casimir effect, discovered in 1948, provides haunting proof. When two uncharged metal plates are placed extremely close together in a vacuum, they attract, not because of any electrical force, but because the vacuum between them is slightly less energetic than the vacuum outside. The plates, in effect, are squeezed together by the pressure of nothingness. The void itself exerts force. The idea that emptiness could push, could act, was almost unbearable to classical intuition. Yet there it was, undeniable, whispering that nothing is not what it seems. Zero-point energy, the residual vibration that remains even when all other motion ceases, is the heartbeat of this nothingness. It cannot be removed, cannot be cancelled, cannot be frozen away. Even at absolute zero, the universe buzzes faintly, humming with the fundamental frequency of existence. It is the sound of the cosmic strings we spoke of earlier, still vibrating in the dark, their music continuing long after the instruments seem silent. To physicists, this revelation was as shocking as it was profound. If vacuum fluctuations exist, then creation itself might arise from nothing. And indeed, modern cosmology suggests that the universe may have done just that. Quantum theory allows, and even predicts, the spontaneous formation of entire universes from the vacuum. Brief, self-contained bubbles of space-time that may expand, cool, and evolve just as ours did. Within the rules of physics, nothing can give birth to everything, and perhaps must. This idea turns philosophy on its head. For thousands of years, thinkers debated how something could arise from nothing. The Greeks invoked eternal atoms. Theologians invoked divine will. But quantum physics presents a third path. Maybe nothing never truly existed in the first place. Maybe the vacuum, this sea of potential, is the primal state, the cosmic mother from which all else unfolds. The Big Bang may not have been a beginning, but a fluctuation, a ripple in the sea of nothingness that refused to collapse. Here lies both comfort and dread. Comfort, because creation no longer demands a miracle. The laws of physics themselves are creative. Dread, because it suggests the ground beneath existence is less solid than we ever imagined. The universe may be temporary, one fluctuation among countless others, destined to dissolve back into the vacuum from which it came. And yet, what a beautiful paradox, that the void itself is alive. That emptiness can think, dream, and wonder through us. The vacuum's energy is not confined to the microscopic world. It fills the vastness of the cosmos. Dark energy, which constitutes nearly 70% of the universe's total content, may be nothing more than the vacuum's quiet pressure on space-time. Its presence is subtle but relentless, accelerating the expansion of the universe with every passing moment. Galaxies drift apart like leaves on an invisible tide, carried outward by the pulse of the vacuum. If this continues indefinitely, the cosmos will end not in fire, but in isolation. Stars fading, matter decaying, everything dissolving into a cold, dark equilibrium where only the vacuum remains. And yet that vacuum, that supposed void, will not be dead. It will still flicker, still hum, still birth fleeting sparks of possibility. Even after the last star has gone dark, creation will continue at the smallest scales. Quantum foam will still churn. Virtual particles will still dance. Nothing will still create something endlessly. To peer into this truth is to confront the strangeness of existence itself. If the void is full, what does being even mean? If the vacuum is the real foundation of reality, are we not made of nothing more than fluctuations stabilized by attention, by coherence, by the act of endurance? Every atom in your body once rose from the vacuum, sustained for a time, then bound into molecules and matter. When you die, those atoms will return to the sea of potential, their patterns dissolving back into the quantum foam. You were never separate from the void. You were one of its songs, briefly sustained in harmony. And this raises the oldest and deepest question. If everything arises from nothing, then what is nothing? It is not emptiness. It is not absence. It is the fertile field of possibility, the stage where every potential reality exists in superposition. Some physicists call it the zero-point field, some the quantum vacuum, some even the mind of the universe. Perhaps all are correct, for at this level, physics and philosophy become indistinguishable. To speak of the vacuum is to speak of the breath between being and non-being, the silent pulse that holds the universe together. Think of it as a sea of invisible light, waves so small, so fast, that they cancel themselves out almost perfectly. Almost. That tiny imbalance, that whisper of energy left over, is what keeps the cosmos from collapsing into stillness. The universe is imperfect, and that imperfection is its life. It's humbling to realize that we exist because nothing is unstable. The laws of physics demand fluctuation, and from those fluctuations, galaxies, planets, and consciousness itself emerge. You, reading this now, are the echo of a quantum tremor that never stopped echoing. So when we speak of nothing, we are not speaking of a void, but of potential. a pregnant silence vibrating with infinite possibility. Perhaps creation and destruction are not opposites, but partners in an eternal rhythm. The universe breathes out matter and energy, breathes in stillness and return. Between those breaths lies the vacuum, the eternal pause, the heartbeat of existence. And maybe, just maybe, this is what nothing truly means. Not an absence to be feared, but a fullness too vast to comprehend. A field of pure potential, so balanced, so infinite, that it can birth entire realities without losing itself. The vacuum is not the end of everything. It is the beginning of beginnings. The smallest thing in the universe, it turns out, might be nothing at all. And yet from that nothingness, everything arises: stars, minds, dreams, and the endless unfolding of time. The universe is not built upon a foundation of substance, but upon the quiet trembling of possibility. The void is not dead space. It is the wellspring of creation, the silence that sings existence into being. In seeking the smallest thing, we found there is no smallest, only endless depth. Every time we thought we'd reached the final layer, it dissolved beneath our hands into something more elusive, more abstract, more infinite. The atom gave way to the nucleus to quarks, quarks to strings, and strings to the trembling foam of space-time itself. Each frontier we crossed revealed not a final object, but a deeper relationship. The closer we looked, the less there was to see, until the search turned inward, and we realized that what we were truly chasing was not matter, but meaning. The journey to the smallest thing began with simplicity and ended with paradox. We started with the dream that the universe was made of tiny, indivisible building blocks, eternal bricks that formed everything. But the deeper we ventured, the more the solidity of that dream crumbled. The quantum realm revealed a world without things, only probabilities. The subatomic field showed us that particles are ripples, not marbles, and at the Planck scale, even space and time began to dissolve into uncertainty. What we once thought of as stuff became movement, vibration, resonance, energy folding in on itself, playing its endless, self-generating song. It is humbling to see how far the question has led us. Every new discovery brought not closure, but expansion, an invitation to wonder. The smallest thing was never a thing at all. It was a process, an interaction, a pattern in motion. The universe is not made of objects, but of relationships, a web of resonances connecting everything to everything else. The quark exists because the gluon binds it. The field hums because the vacuum stirs. We exist because the universe cannot stop asking what it is. Perhaps this is the true revelation. The smallest thing is the question itself, the act of looking, the desire to know. Each layer we uncover mirrors our own hunger for meaning, our own capacity to reflect. The deeper we go, the more the universe seems to turn its gaze back upon us, as though it were aware that it is being seen. What if consciousness, curiosity, and existence are not separate phenomena, but one continuous loop, the cosmos exploring itself through us? It is said that the universe began as a fluctuation in nothingness, but maybe that fluctuation never ended. Maybe the Big Bang was not a single event, but an eternal process, the universe forever emerging, moment by moment, from the vacuum of possibility. Every atom, Every photon, every thought is part of that unfolding, a brief crest on an infinite wave. The question, what is the smallest thing, might be the universe's way of hearing its own echo, an inquiry so profound that it sustains creation itself. And so, we end where we began, in wonder. Beneath all our measurements and mathematics, beneath the elegant symmetries and shimmering equations, lies mystery. The universe is not a static structure to be solved, but a living poem, constantly rewriting itself. The Planck wall, the quantum foam, the vibrating strings, they are all verses in a song too vast to end, too intricate to resolve. We can trace its melody, but never its source. When you look up at the night sky, you are seeing not just stars, but reflections of the same vibrations that make your atoms hum. The galaxies spinning in the dark are echoes of the same forces that bind your heart together. The smallest thing and the largest thing are not opposites. They are mirrors. The infinite hides within the infinitesimal. The cosmos is folded within you, and you are folded within it. Perhaps what's most fundamental isn't matter, but meaning. Not particles, but participation. The universe exists not as a collection of things, but as a story. One that tells itself through every atom, every star, every question asked by a curious mind. We are part of that story, a brief awareness in the great unfolding. And maybe, in the end, that's all there ever was. Awareness, shimmering through form. The smallest thing was never hidden in the depths of matter, but in the act of seeking itself. The question is the answer. The looking is the finding. Because in the search for the smallest thing, we found that everything, every quark, every photon, every thought, every heartbeat, is connected, continuous, inseparable. The smallest thing is not beneath us. It is us. It is the universe, looking back through our eyes, and somewhere, beyond measurement, beyond knowing, beyond even space and time, the cosmos keeps humming its endless song. The vibration that began before beginnings, that will echo long after endings, a single, eternal note of wonder.